Yep, so now we've seen for general Hamiltonian, what is the best state to use for the fish information to sense signal generated with this Hamiltonian. One last thing maybe we can see is the optimal. One last thing we can see is the optimal measurement. So there's right. You remember that we also discussed this point that when we get the SLD, do you remember this? The SLD also gives us the optimal measurement to use. Yeah, because when you construct the fidelity, you get the optimal measurement for discriminating state. Then the SLD gives the optimal measurement to get the Fisher information, you know, as a classical fish information of the outcome probability distribution. So maybe we can just look at this first because it might be important for later. So let's just look at the state and also consider now use our SLD formula and look what is the optimal measurement to do. One thing we can do here is we see why the qubits are so important that to get all our intuition, we'll just, you know, this is a qubit state, right? Because it just involves two things. So let us just call S min equal to 0 simply, and S max equals to 1. And then we get our usual Pauli matrices and everything. Okay. Yeah, so let's take our SLD formula, which we just derived before, and compute it like this. In fact, you did it probably already in the exercise for the qubit case. But I can just illustrate the formula now. So the formula was we derived in the first hour, it was telling us that the SLG, let me find it, the state which, so L, so L is equal to 2 times I, and then we had sum of K and L, and then only taken indices where both eigenvalues are not simultaneously 0. All right, of Pk minus Pl divided by Pk plus Pl times Hamiltonian KHL and KL. Okay, so let's see what we have now here for our state. So for our state actually is just a rank 1 state. Right? So if you look on the basis where it's diagonal, there is actually just psi opt, which is 1, and then all the other states which are orthogonal. Right? So when we look at the sum for all values where both coefficients are 0, it means that actually it's a single index sum, right? Or in other words, I can write it as equal to 2i sum of, I will just fix k here. Let's look on the first one. So p is 1, right? P is always, so again, there is just one p which is not 0 because we have a pure state. It's a p, kind of the p0 which corresponds to the state itself, psi opt. So this factor will always be 1 minus 0 and 1 here. So it will always be 1. So the only thing which is important is this guy here. And then we get psi opt H. Okay. And then we have somewhere L. So now L covers all orthogonal states. And psi opt L. Yes. Okay. Plus the other one, which is L, H, psi opt, but with a minus sign now, because now K, now we use L, which is 1. So this is a minus sign. Yep. Psi opt. Do you see what I'm writing here? No? And then we get L, psi opt. So I'm just using this formula for our state, taking care of the sum of this condition here, and the summation indexes. So now if you look on the state, yes, so let's just look on this expression here. Right? So we have sum over, so let's just take a look on this expression. We have psi opt, sorry. So psi opt is the set of psi opt, so okay. Psi opt H over L, sum over L. So for all possible L's, right? L's are all orthogonal states of psi opt. So if you put it explicitly now, well, we just have psi opt in our qubit basis. This is simply 0 plus e minus I phi 1, right? Times the Hamiltonian times some other state. Hamiltonian because the Hamiltonian gives minus delta 1. So this thing is, we get minus, you know, the Hamiltonian, remember, it's delta over 2 in the qubit subspace. So we get minus delta over 2, 0 plus delta over 2, 1 over some state L. Okay? Or in other words, this is minus delta over 2, 0, minus 1 times some state L. So you see that actually this is a pure state. It's actually a pure state which is orthogonal to our state here on the equator. So not orthogonal, but which is in a conjugate basis. Right? No, it's actually orthogonal. So so basically we can construct a basis where there is a single state L, which is, and there is a factor of 2. Sorry. We can just take L to be the state, it's well normalized, and then it will be a single term in the sum. Right, so I will do this now. So we identify here the L, single L with a single state with which this psi of H has an overlap, so that it's 0 for all other L's. And then from this formula we get what? Well, we get our SLD expression, which is then given by, so L is equal to 2I times, this will be 1 because it's normalized, times delta over 2. And then we have a state psi of, so which is 1 plus I phi, sorry, 0 plus I phi 1. And then we get 0 minus I phi 1. I'm correct. Okay, and for the other one, for the other term here, we just get the opposite term with a minus sign. So we'll get minus 2I. Okay, 0 minus I phi 1 and 0 plus I phi 1. Okay, I guess this was a bit hard to follow, this computation. But the idea now is what? Is that we can open this thing here, and there is also a factor of 2, because there is another factor of 2, which comes from the normalization of the state. So I just erase this 2 here and there. So, but now if you open the brackets, you see that 0, 0 goes away with this 0, 0. All right. 0, 0 goes away with this 0, 0. 1, 1 also goes away because here it comes with a minus sign, here it comes with a minus sign as well. So the only remaining terms are the cross terms, and the cross terms they give us, this is equal to I delta over 2 and this one times this one, so e to the minus I phi 1 0 and 0 minus the I phi 0 1 and 2 times, because this parenthesis will give us the same thing. Okay, so I presume it was a bit hard to follow this computation, but but let's see what, for example, let's see what so just to complete this, let's see what we get for the case of phi equal, for example, right? So let's say phi now equal, this is the SLD, right? Let's say phi equal to 0, right? So this state, then psi opt is a plus state. So we know the psi opt is on the equator here, right? This is opt psi, the initial state. And what is this thing then? Well, this thing, you see that this is actually a sigma y, right? So we just have I, the coherence, right? So for this, for phi equals 0, we get something proportional to sigma y. What does it mean? It means that if the original state is here, then the optimal measurement is to measure in the y basis. And so I prepare the state here, then depending on z, and then depending on the value of b, it will rotate around the value b equals 0, right? Because here within, and then I will measure in the y basis, and this is how I can detect. This is, you can annotate the Fisher information. We can do this explicitly, actually, right? We'll do it explicitly later on. I think it's a good idea to just compute these probabilities once. So, yes, that's the point. The point of this computation, which I messed up a bit, is that if you have an optimal state somewhere on the equator, right, this is what we have here, then the optimal measurement is the orthogonal one. Okay? So good. Now let's look at what happens when we have many probes. So let's forget this. Now consider this would be part 2. There's a single probe 2, so many probes in product state. In fact, it's not difficult in a product state. Now we really have many probes here, n probes, and we consider a general, so an original initial state. The initial state now is psi, which is just given by some tensor product for I equal to 1 to n of some state psi I, right? The question, of course, is the same. What is the best Q phi? What is the best quantum fish information we can get with the product state? Do you have any thoughts about this? But do you remember we proved something about fish information, which is nice about product state? Do you? Well, so one thing is that we've seen that it's additive on products, right? So if you have like independent states, then the fish information on the total state is just additive. So it's clear already from the beginning that this fish information will just be n times the fish information of the single state. But let's just do it explicitly, maybe for clarity. So let's look again the same thing. We just consider the variance of the Hamiltonian. This is a simple exercise, so for later maybe we'll get some hand on it. So, well, the best state again is the same thing. We just consider the variance now of our collective Hamiltonian on the state side. Yes. So what it is, this is just h squared again minus h squared. All right. Now this time let's start with h. And h is with a psi, right, our global state here, and we have here sum of I, h psi. Yes, and of course, when we do this, this is nothing else than just the sum of I of psi. So the expected value of psi a, and now here it's clear that basically this thing acts as identity on the other ones. So this is simply just the expected value of hi on the state of the ice particle, right? So this is just the sum of I of hi expected value for the state. Okay? Clear, right? Or so we have a tensor product here, but of course we have identities on all the others. So the tensor, when we have a product between I which doesn't match the Hamiltonian here appearing in the sum, we just get 1, and for the others we get, for the I we get the expected value of the Hamiltonian for the state of the particle I. Just this is basic things, but I want to be sure that it's clear for you how this goes on, right? Yep. Good. So we're good. Now, what is a square? Square is a bit more tricky. So what is h squared expected value? Well, this is psi again, and then I have a double sum now ij of hi ij of psi. Now I have to distinguish two cases. All right. So one case is where I is not equal to j, and one of it is equal. So when they're equal, we just get psi, and here we get sum of I of hi squared, right? So hi plus we get sum of I is not equal to j of hi hj on the same state. Now, if it's equal, it's just, again, as before, we just get the absolute expected value. So sum of I, the expected value of hi on the I system square. Whereas not equal, since we have a product state, the expected value is just the product of the expected value, right? So that's sum of I j not equal to j of hi aj. Yes, and this is precisely here. It's important. We can write this expected value of the product as this thing only because it's a product state. There is no correlation between this h on ith particle and h of this particle. Good. So finally, if you make the difference of the two, we get the variance is h squared minus h squared. So this is sum of hi squared. Sorry, hi squared plus sum of ij hi hj minus hi sum of I squared. Okay. Again, now we just open the bracket and we get a result. Because when we do this, if I open the bracket again, just the sum, we can again just say the same I, which is hi squared plus this thing here, plus the different term I not equal to j of hi hj. Yes. So minus this, plus this thing here, and you see that these two terms cancel each other, and then we just get sum of I of hi squared minus hi squared. So for a product state, the variance of a product state is just the sum of the variance, sum of I of variance of psi I of the Hamiltonian hi, which is not very surprising. Actually, the equals. It's clear. Yeah, so what we prove here now is that for the fish information of this product state, so the fish information is QFI of the product state, quantum fish information of the product state is given by f of this, let's do it like this, tensor product sum of the fish informations of individual state psi I of I, right? And clearly now we identify the best one. So we know that, so to optimize the thing of the product state, we just optimize individual component, right? And then we just get this is small equals than n times delta square, right? So where delta square was precisely the spectral range of the local Hamiltonian for each particle. Yes, so this is the important thing. So you see here, if you have a product state, the fish information just scales linearly with the number of particles. Okay, that's the thing to remember. Maybe one comment on this is that you remember that fish information is kind of convex. So in other words, fish, if you have, right? I don't know, did we prove it or not? Maybe we mentioned it. For me, it's actually very easy to prove. Maybe. Are you aware of this? So fish information is convex. What does it mean? I mean that if you have to convexity, if you have a state rho b, right? The curve rho b and then the curve sigma of b, then the fish information of the mixture of the two states, rho b plus 1 minus p sigma b, is smaller or equal than the sum of the fish information, average, rho b. Does it sound trivial to you or not? I put it explicitly in the script, but it really follows just from the concavity of the fidelity, right? So if you mix two states in the fidelity, then it can only increase. So fish information can only drop. Okay. So what does it mean now here for this thing is that it means that actually for this bound here holds not only for pure product states, but also it holds for mixtures of all product states. Because if you start mixing these product states, we cannot exceed this thing, right? The fish information alone in general will just be lower. And the mixture of all product states is precisely given by like this defines a set of separable states. So for all separable states where there is no entanglement whatsoever between all the polar probes, the fish information is bounded by this quantity here. Yes, and we will discuss more about entanglement and how fish information is connected to entanglement in future lectures. So yeah, this limit sometimes is called the standard quantum limit. Standard quantum limit. Yes, because it actually gives us, if you look at the precision now, which we get, so this mean squared error of the estimator, right? It gives that this mean squared error goes as 1 over n. This is the variance of the estimator. So if you look at like the error, the standard deviation, then we will get the square root. And this is why it's called the standard quantum limit. This is kind of just repeating n independent measurements, right? Yes, good. Finally, now let's look on what we can do, how we can do better if we allow any states. Yes, and this is really kind of nice thing about quantum metrology. So 3, general, the optimal states. What is the what is the optimal states? What is the state maximizing QFI? Okay. So how do we do this? Well, actually, we solved it already almost because we know, so because our global, so okay, I make the drawing again. So we have now we have our probes, right? We can prepare a global state psi, and this will just interact with the global Hamiltonian, yeah. And then we have measurement, a global measurement potential on the scene. All right. So question now, what is the best state to pick? If we are allowed to pick any state, not just product state, but any state in this Hilbert state, what is the best state to pick? Well, but clearly we already solved it because we know how to connect the best state to just the spectral properties of the Hamiltonian. Now the only thing is that now we need to consider the global Hamiltonian, not the local Hamiltonian. So let's do it. Now we just recall that this H is the sum of all HI's, yes, for all parties from I to n. So what is the spectrum of this Hamiltonian now if we look at it? Well, it's also clear because we can very easily identify the external values of the thing, right? Recall that HI is an Hamiltonian which has minus delta over 2 here and delta over 2. Okay, and the states correspond here to, we get S max, sorry, S min here and S max here. All right. So any idea what would be the minimal possible eigenvalue of this state? Of this Hamiltonian, yeah? Well, first of all, let's just take what is the eigenbasis, right? We know that this state is this Hamiltonian. We have a local basis which diagonalizes it, right? So what will be a global basis which diagonalizes the global Hamiltonian? Well, this is easy to see because we just get, this is just a sum of our local Hamiltonian. So whenever we act with the local Hamiltonian on the state, and we want to have the same state at the output, we have to have an output, and we have to have an eigenstate here. So basically, it means that if you have a basis which is eigenbasis of this Hamiltonian, then the global basis diagonalizing the Hamiltonian is just the tensor product basis of the local basis. Yes. Yeah, you just easily check it. It has to, because they all act differently on the state. Finally, now it's also clear to see what is the minimal one, because yes, so if you take a state, now take a general state psi, take a general product state, so we just psi I. Now if you act on the state psi 1, psi n, if you act on the state with our Hamiltonian H on psi, yes, and we assume that all these psi's are eigen states of local Hamiltonians, then we just get sum of HI's, right, acting on this tensor product, psi 1 to psi n. Well, the eigenvalue will just be the sum of the eigenvalues, yes, because each I will act on the one, so we'll get kind of lambda I, sum of lambda I over I on the state psi. So if you want to find the minimal eigenstate of the global Hamiltonian, so the minimal eigenvalue of the global Hamiltonian, we just have to basically have a sum of eigenvalues for all states. So we basically pick the minimal one for each individual Hamiltonian. So clearly the minimal one then is given by minus delta over n times n, yes? And this is attained by the state. And now if you see it here, maybe let me just This is obtained by the state, which is just the tensor product of S mean of all i's. Yes? And the maximal, again, is just equal by plus delta over 2n. All right? And this is attained by the product state, which is S max of all parties. Is it clear? Yeah? I mean, it's pretty simple. So, in summary, now we also find, since we know the spectrum of this Hamiltonian, the global one, right? We can just reconstruct it from the spectrum of local ones. And actually, we only care about the extremal ones, so we don't care about what happens here in the middle. The extremal ones are just, okay, pick the minimal eigenvectors for each hi, or pick the maximal eigenvector for each hi, and this gives the extremal for the sum as well. Yeah. So what do we get? So we get that now our state, so the optimal state psi opt, since we found the extremal eigenvalue, this is equal to 1 over square root of 2 of tensor product of all states S mean for all i's, I equal to 1 to n, plus some phase factor, which phase factor is not important for the variant, I equal 1 to n, the tensor product of the maximal eigenvalues of all i's. Okay? Which follows from this spectral decomposition of the global Hamiltonian. And the fish information, so the fish information of the state, psi opt now, let's put psi opt global, so some g maybe here, just to avoid the confusion. Well, again, this is just the variance of this one. Right, so you remember, so basically it just means that we replace delta, right? So we just take, so this Hamiltonian is like taking delta prime minus delta prime over 2, with delta prime equals to n delta, all right? This is the same thing here. So this fish information is delta prime squared, since we computed it already for the previous thing, and this is just n squared times delta squared. Yes. Right? Do you agree with this?
Yes.
Yeah. So again, if you go back to our identification, put in S mean 0 and S max 1, then we can call this, so then the state is, I will just write it once. So this is actually called a Greenberg and Hornet-Zeilinger state. So the form like 0, all zeros, plus phi, all ones. All right. And the fish information is equal by delta squared times n squared. Now, one thing you can see already is that obviously this is not a product state. Actually, it's very far from a product state. This is kind of because they have maximal correlations, right? It's really either, it's kind of like a Schrodinger cat state again. So either we have like all the spins pointing up, or we have all the spins pointing down. So it's kind of a superposition of maximally different state in terms of total spin. So it's actually, it's kind of a very quantum state in its nature. And again, we'll see what it can mean in the future. Yes, so what's the time? Yeah, so we still have some time. So first, let me just summarize this. And now we have these two different, very different scalings. So remember that we had product states, and for them the fish information is just goes as n times delta squared, and this is called standard quantum limit, SQL. And now we'll identify the best possible quantum states, so the best possible entangled states, GHZ states, and for them the fish information is, it goes as n squared times delta squared. Yes, and this is usually called the Heisenberg limit. Yes, so you can directly see that, of course, if you really want to, in practice, to sense something, some field, you know, and you just have a small system with, I don't know, n atoms there, or really n decenters, then if you're able to prepare these states, well, you can really, you can get an estimator much better estimator, right? And moreover, it's not just a constant prefactor, but it's a prefactor with scales with n. Yes, because of course we can just use the crime error bound, we can translate it into the mean squared error of the estimator. So this is kind of a slide to remember if you from this lecture. There's really these two different regimes. So like that, actually running out of time a bit. There are two things we don't have time to see all, but there are two things we could see, and they're both important. But I think the other one is more important. And the other one is, so we see that having entangled probes allows you to boost the precision of the estimation scenario, right? But now the question, of course, is what kind of measurements do we need to do this? So is it also true that so once we have this GHZ state, so now let's say we have these probes in the GHZ state here, they prepared in GHZ state, then they interact with this Hamiltonian, and then, well, QFI just tells us just the property of the state, and then but we will need to know what is the optimal measure to do this. Okay, and let's just do it quickly with an example. No? But I want to show you that actually, in fact, we don't need. So in principle, you could need some crazy measurement here, which is entangling. So projection on some entangled states of the particle, but actually you don't need anything like this. It's enough to measure just locally. Okay. This is also important for practical applications. So let's see what's the best possible measurement. And for this thing, we will. Yeah, well, I'll just consider our GHZ state, which is of the form. Now, let me put an I factor. So we take the GHZ state, which is like this 0, 0, 0, 0. Right, so many zeros here. Plus I 1, 1, 1. Yes. So that this state is really kind of pointing here in the y direction on the block sphere. Yeah. Not in the block sphere, but again, so now it's not a block sphere, but now we can also define a virtual block sphere with just saying that this is 0, 0, 0, all zeros, and this is 1, 1, 1, all ones. Yes, just say this is kind of a global one state, global zero state, and global one state. Yeah. Now, for what we have seen, if the state points in this direction, the optimal measurement is in the x direction. So the optimal measurement then, right, which we can obtain from solving the SLD for the state. Optimal measurement is x. It's an x operator, and this is given by the following thing: 0, 0, 0, 1, 1, 1. So the coherence between these two elements plus 1, 1, 1, 0, 0, 0. Yes. This we can just directly conclude from the SLD. But the question, of course, is it? Can we measure this thing? How do we measure this? Let me see how I want to prove it. Well, yes. So one thing you can one thing we could one way to check it is that if you look on this operator here, yeah. And we can let's compute how its commutator is the big operator with the tensor product of all sigma x operators. Yes. So tensor product of commutator of x with the tensor product of all sigma xi operators. And this, if you look at it, well, clearly what happens here is that yeah, let's just compute the product first. Commutator is too long to write. So x times tensor product of sigma xi operators, right? Equal 1 to n. Well, if you act with the thing, so you see sigma x, it flips all the ones to all the zeros, right? So here it's a tensor product of all x, so it will just flip all of them. So in other words, we get, if this thing acts on the left on this term, well, we get 0, 0, 0 times 0, 0, 0, yes? And if we act on this term, we will flip all the ones to ones, okay? And now you can see that this thing is the same as if you do it the other order. I equal 1 to n, sigma x to 1, I. So this two operators, this one and the tensor product of sigma x, they commute. In other words, they can be measured simultaneously. But to measure this thing, we can just measure x's locally. So because this commutator, right, this is two operators that commute, they can be measured in the same, they're commeasurable. In other words, we can just measure the eigenbasis of this one, and this will also be, we can, because they have the share the same eigenbasis, measuring this allows us to construct the values of this operator. Right, so this means that because it's zero, that we already see that basically measuring x is not different from measuring all sigma x locally. So measuring sigma x, the tensor product of sigma x locally, just measuring the parity, it can be done locally. Just measure x's and combine the eigenvalues. But maybe it's, so this is already showed you that we don't need entanglement, because you can measure in the SLD eigenbasis by just measuring local x's with this state. Of course, it will be a different phase. You will just measure locally different bases. But maybe let's just completely explicitly do the same now. Huh? So to have some, so let's just compute these probabilities. 5 minutes. Okay, so let's just compute these probabilities, and so we really define now a state where we say let's measure all qubits. So we have all qubits, they interacted now, and then we'll just measure all of them in the x basis, and we see what is the probability to observe, right, this outcome. So let me now define kind of the product state in the x basis. I will just write it kx, x meaning that it's x basis. This is the state, right, which is the tensor product kx. Right? It's a tensor product of I equal 1 to n. Let's say k, each ki now is either 0 or 1. So this k now is a bit string. So it's like a long string of zeros and ones. So it actually gives us the measurement outcome and the x measurement for each party. So it can take 2 to the n values. And now we say that this kx just by definition takes 0 plus minus 1 to the ki, the bit ki 1 divided by square root of 2. Yes. So really then just each kx is just plus minus, or no? Just gives plus for some party and a minus for some party. And really the vector of zeros and ones gives us where we have a plus and a minus. Yes? So measuring this eigenbasis, really it's just like measuring each party in the x basis and then sending the outcome to the central station, or yes, and constructing the k. Yeah? So just putting this outcome all together. So let's compute the probability of having such a measurement. Yes, so what do we get? So if you do such a measurement, what is the probability of the k outcome, of the outcome kx given by the b-string? Well, the probability to, which is given by the overlap, so we have pure state, so we just get kx times jhz. Yeah, sorry. But of course we need the encoding here. So times u, the encoding b on the jhz. Here, right? This is what we need. So this will just denote it as, so this is the j effect on which we acted with our field. We'll just write the jzb. Okay, and you see that, yeah, okay, sorry. I'll just write this in. So jzb, I forgot to write jzb. This is EHB acting on our jz state. And this is clear because now we just here we get, remember that Hamiltonian is minus delta n over 2, delta n over 2. So this state is 1 over square root of 2 e to the minus delta n over 2 with an I, 0 to zeros, plus I pi over 2, this is for the I factor here, plus I delta n over 2 and the b, and the 1. Okay, it's very nice. Right, I just applied the Hamiltonian on the state. Okay. One thing is that I don't like this pi factor, so we'll just factor out the pi over 4. So we'll just write it down as false. This is equal to 1 over 2 pi over 4 times minus I of delta n over 2b plus pi over 4, right? plus to the I delta n over 2b plus pi over 4. And this is all zeros to the n, and this is all 1 to the n. Now wait a second, guys, we'll just close the door there. Are you here?
Yeah.
Do you mind if it takes 5 minutes for the end of the lecture? I mean, you have
no problem.
Fine, yeah? Yes. So, yeah. Sorry, I don't know why it takes so long this computation. So yeah, and then the only thing I want to tell you is that from this and this JHZ after equality, so the JHZ where the B is equality, right? It's, we forget this global phase again. Doesn't matter. It's 1 over 2 exponential of minus I of this thing delta n over 2b plus pi over 4. And let's call this angle alpha, for example, right? 0 to the n plus I alpha to 1 over n. Yeah. Now with this we can easily conclude on the k things. So let's compute the probability now to observe the k bit string. So probability to observe the k bit string now is kx pick GAZ of b squared, and now what do we get here? We get this tensor product, so of I of 0 plus minus 1 to the k 1 root 2 times our JHZ B. Okay. And you see that since JHZ only involves zeros and ones, well, from all this big product, we'll only pick the terms where all are 0 and all are 1s. And all are 0 is simple. So when all are 0, we just get this phase factor. So in other words, in this sum, we get first the n here, 1 over root 2 to the power n. Yeah, we get a factor of root 2 for each one, and 1 from the JHZ, so n plus 1. All right. And then we get all the zeros, so minus I alpha from the zeros, and from the ones, we get plus e to the I alpha. However, we pick a minus sign depending on whether this ki is 0 or 1. Okay? So here we get something like minus 1 times the sum of I equal to 1 to n of the chi I. Yes? So chi I is the value of the outcome 0 or 1 for the I party. So let's just, this we can call it just the parity of k. Okay? So we'll just call it this is the parity of k. Kx vector. Yes, good. So let me just write it down, because here you see the cosine and sine appearing. Yeah? So in other words, we get for p of kx, this is given to by the square. First, we're going to put 1 over 2 to the power n, put it out, right? And then here we get, if we square it out, we have the absolute value of this. And you see that depending on the sign here, we get either the cosine. So if this minus 1 is not there, this is a cosine divided by 2, right? Cosine square. Or the sine square. So, is it correct? No, just practice it. The simplest thing to do. So we get cosine of alpha plus I sine of alpha, right? Plus the minus here, right? From this expansion, minus 1 to the sum of k i's, and cosine of alpha minus I sine of alpha, right? Squared. So if I is if so, we get this thing is equal to 1 over 2 to the n cosine square of alpha if sum of k I is odd even, right? If it's a plus here, or we get 1 over 2n sine square of alpha if the sum of ki is even. Yeah, and yes, that's the probability that we get. Yes, and remember that alpha was what was alpha? This line. Alpha was n delta b minus pi over 2 O2. That's thing. Right? Well, the final thing is that, okay, let's, one more minute, let's, well, we can just compute the Fisher of the thing. So the Fisher of the thing, just classically, we just remember that the Fisher information for this measurement of this P of Kx, right? This is just the sum of all possible outcomes Kx of this P dot Kx divided by P of Kx squared. I don't know, maybe we can just leave it with the exercise. But yeah, you just derive the cosine and it's kind of easy. So maybe it doesn't make sense to do it now. Let's do it in the exercise. Because it's probably more important to compute. So indeed, yeah, we see that this will, if you do this calculation properly with the probabilities that we just compute, we did get this n delta square, n square delta square Fisher information, which is unattainable with local measurements. Yes, so we don't need local measurements. We don't need entangled measurements to get this precision. We just can estimate with local measurements. Actually, even more, we can estimate with a collective X. We can make an exercise on this as well. So there are two things to say more. First is that, of course, this is really nice. This is really why an example where you see that using generally quantum states, like these JZ states, can boost enormously the precision of estimation of a magnetic field, for example, or of many other quantities. And it really only requires entanglement in the state preparation. So when we measure it out, as you will see, we can only do the collective measurement of sigma x and reconstruct an estimator. Now, what the problem with JHZ states is that they're very fragile. Okay, they're very fragile. For example, you can see that if you have a JHZ state, let's take a JHZ state, right, like this, 1 over 2, and let's say we lose one particle. Do you see what will be the state if you lose the first particle? So let's say we take the state here, and we trace out the first particle. Well, tracing out the first particle is like, we have just like projection on 0 plus projection on 1. So we'll just get a mixture of 1/2 the remaining states, the remaining n-1 qubits in state 0 plus 1/2 the remaining states in the state 1, right? This will be kind of rho JHZ if we lose just one particle, lose 1. Easy to compute, right? Just trace out 1. You see that this state is not sensitive to the Hamiltonian at all, because it's an eigenstate of the Hamiltonian, right? It's really just a mixture of the extreme two eigenvalues. And this shows you that this JHZ state is very, so ideally this estimation with the JHZ state is the best you can do. Whenever you have some imperfections, typically, it's also very fragile. So it will lose all the information encoded about the parameter very fast. For example, in one particle completely makes a state which is just useless for estimation. And even if you just already encoded some phase here, it will just disappear. That's why in practice, actually, JHZ is not only very difficult to prepare, but also it's very fragile, so people will not use it. But there are states like spin skew states, which you'll now see in the exercises, and you computed something with them, where you do have an advantage for the precision, but you don't have such a fragility. And in experiments, people typically will go for this kind of states, all right, to do quantum metrology. Yes, that's the concluding remark. Do you have some questions? No, it's all clear.
Yeah, just a question on that final state. We say that we lose sensitivity or interaction with the actual Hamiltonian because we get rid of the extremal points. That's how I see it, at least. Because in the end, we have these. We remove a single a single state, a single particle, basically,
Yes.
and the extremal points in the global Hamiltonian, we can't actually measure those anymore. Well, that's how I kind of see it.
Well,
I don't know if that's correct.
I wouldn't say it like this. I think it's things that the intuition will be different from my perspective. Is that the state has extreme like quantum correlations between all the states, right? So like if it's the usual thing, right? If you have like an entangled state between two systems, you trace out one, the other one is mixed. So
Yeah.
this state is such that whenever if you lose a single particle, the other ones are completely, because each particle knows exactly the state of the other particle. You see, they're completely correlated. So this first guy, if it's in a zero, it knows that all the others are in zero as well.
Yeah.
So whenever you lose one single particle, you kind of collapse all your superposition, which give you big variance. It's just a mixture.
Okay.
The external points. So you still kind of get the external points for the other ones because you get this. But now the point is that it's not superposition of all zeros and all ones. It's just a mixture of all zeros and all ones.
Okay.
Right. And this state, it's just a mixture of eigenstates. So clearly, like, it doesn't encode any information. Because if the information here is really encoded in a relative phase between the two, right? So that's what we've seen before, right? There was like a phase difference between the two, and this phase difference is what encoded the parameter.